Hey, good afternoon, everyone. Hopefully everybody is awake. Yeah. My name is Srinivas Kolluru, and I'm a senior director at JB Hunt. My team is responsible for the enterprise architecture, and we cover all the applications, data sciences, and even infrastructure and operations. So that's me.
I'm Donovan. I am one of Srinivas's lackeys. I architect the visibility for JB Hunt, and that's what I do.
Yeah. Okay. So during this discussion, I would like to talk, give something about JB Hunt, what we do, and also talk about the industry challenge. I'll give you some stats on the scope and scale of the problem, because a lot of times people don't understand what the transportation logistics industry is and what type of challenges we have. Because obviously coming from the CSX team presentation, our problems are almost the same, whether you call it the railroad or trucking or intermodal, whatever you want to call it. Okay. Then I will hand out to Donovan. He's going to talk about some cool stuff, what we have been doing, and high-level architecture and implementation. He's going to talk about some of the lessons learned during the implementation and go through some numbers, and if the time permits, we would like to do some demo also. Okay. Just talking about JB Hunt. JB Hunt was founded in 1961. We just celebrated 60 years last year. It was started with 5 trucks and 7 trailers, and now we are a Fortune 500 company with thousands of trucks, thousands of trailers, and 100,000 plus containers. We are the largest asset-based transportation company in US. We are big into sustainability. We take it very seriously, the sustainability and other stuff. I'll talk about some of the numbers and everything later on. One thing that I would like to mention about JB Hunt is JB Hunt has a reputation of disrupting the transportation industry. We were the first ones to offer, as a major trucking company, the intermodal services. Okay, we have partnerships with major railroad companies, and our biggest partner is BNSF. And we also recently announced increasing the intermodal capacity by 40% due to sustainability and other things we are going to talk about. The second one is JB Hunt has gone through a digital transformation over the last 6 years. 6 years back, we were a traditional trucking company, but now we are considered a technology company. Everything is done in cloud, and everything deployed with Kubernetes, and our technology stack is almost the latest and greatest you can think about. With that, visibility is one of the challenges in the transportation logistics industry. When you talk about supply chain or transportation logistics industry, visibility is one of those key ones. And having the complete visibility is critical for reducing the cost, time, and also providing efficient carbon-friendly transportation logistics. Let me give you some numbers here. Let me pause and talk about some numbers. 72% of the freight in US is moved by trucks, 72.5%. They may go on the trains, but ultimately they end up in the trucks, okay? And trucking is a small business, ruled by small business. 91.5% of the carriers that we have 6 or less than 6 trucks, 91.5. 97.4% of the carriers have 20 trucks or less than 20 trucks. Think about it, 97.4%. So that leaves rest of the 2.6% for companies like JB Hunt and other people. So trucking industry is dominated by small businesses. And given that these companies are so small, most of the business happens through Excel spreadsheets, whiteboards, and then the phone calls. So the drivers are not as sophisticated as you want to be. They don't want to use our app, but they will take the phone calls and they will drive for you, okay? And it's all based on relationships. There is also, you heard all kinds of things about supply chain and the challenges with the supply chain. In 2020, according to DOT, there are 4 million Class A commercial trucks that are registered, whereas we have only 3.4 million drivers. So just from truck to driver ratio itself, there is a 600,000 driver shortage, even if you put 1-to-1. And because of the COVID, it even gotten worse recently. So we have a severe driver shortage. That means keeping the drivers happy is very, very important. Making sure they are getting paid is very, very important. And making sure they can have enough downtime and time with their families is very important. That's where some of this visibility also comes into picture. And another one that I want to quote is 92% of food, especially the vegetables, fruits, and then any leafy vegetables other than green vegetables and dairy depends on trucking. 92% of dairy and vegetables. So if you see the empty shelves in Walmart and other places, you know why. Because of driver shortage, there are no trucks, and 92% of that industry depends on the trucking. And 65% of the pharmaceutical industry depends on trucking. So I'm bringing these things because that will help us talk about IoT, because some of these pharmaceuticals and fruits and vegetables need to be driven in a temperature-controlled trailers. And keeping the temperatures, the right temperatures, is critical for delivery and also for cost and money savings. So lack of visibility, cost, time, and money, I talked about it. There are a couple of things that I want to stress, is that 30% of drivers' time is spent in detention. The detention means either they are looking for loading the goods or unloading the goods, or they are trying to do the paperwork, or they are trying to find the equipment. They go to a yard and they need to physically meet somebody, and they say, like, go to yard number 4 and pick it up. They need to roam around in order to find the trailer and pick it up. And drivers are paid by the number of miles they drive with the freight. If there is no freight, they don't get paid. So in addition to the detention times, there is also empty miles. Drivers typically drive 50 to 100 miles going to a location for picking up the freight. They don't get paid for that. So having this route optimization, network optimization is critical, so that the drivers spend less time looking for the equipment and less time driving the empty miles, so that they are getting paid. Just imagine, like, 30% of the time is wasted, means they are getting 30% less paid. And on top of that, federal government has regulations. You can only drive 11 hours in a day out of 14 hours of total. So your job could be 14 hours. You need to have mandatory 3 hours breaks, and then you can only drive 11 hours. And you need to have mandatory 8-hour break to drive the next day. So there are all kinds of restrictions, and losing money on top of this because of the wastage is going to hurt the drivers. And that's where this visibility comes into picture. And then complete visibility, and again, makes everybody happy. That's where JB Hunt has done a lot of work on route optimizations, network optimizations. And also, if you use our marketing platform, marketplace platform, we provide recommendations for the carriers based on their previous behavior, and also we create the routes. So for example, I'm looking for something to drive next Monday, and I want to come back home Thursday afternoon because Friday is my kid's birthday. We can tell you, hey, you have 4 days, and your behavior is you go drive to Chicago and come back. So you start in Dallas, you can go to St. Louis, drop the load, pick up the load, and then drop it in Chicago, and come back from Chicago to Dallas in 4 days. That way, you can be with your family on Friday. So we have a lot of those optimizations, recommendations going into our marketplace that will help the carriers. The next one that is receivers are interested is the arrival times. We have customers that want to know when the freight is arriving at their distribution centers. Some customers want 15-minute notifications, 30-minute notifications, so that they can have the staff ready for loading and unloading the goods. So we use a lot of geofencing, and as soon as you break the geofence based on the customer requirement, we send the notifications. Okay. Sustainability is very important to JB Hunt. We are kind of pioneers when you think about other companies in the sustainability. Just through our routing and network optimizations, since 2020, less than 1.5 years, we saved 6 million empty miles. And the next one is safety, very important to us. We just celebrated last year one of our drivers completing 5 million miles without any accident. Imagine a driver driving 5 million miles without any accident. And at the same time, as you can see, there are 116 drivers of JB Hunt that finished 2 million miles without any accidents. The middle one is also very near and dear to us, reducing the carbon footprint. And as the CSX team know, using intermodal is 2.5 times efficient than using the truck, and it reduces the carbon footprint by 60%. So JB Hunt, by moving the shipments from trucking to intermodal, we saved in last year itself 3.5 million tons of carbon emissions. And as I said, we recently announced a partner increasing the intermodal capacity by 40%. So that should even decrease the carbon emissions because we can ship more freight through train, not through the trucks. I just want to give you some of the numbers. These are the numbers of JB Hunt owned equipment. We do have 100,000 carriers that we outsource that are certified. So if you want to work with JB Hunt, you need to go through a certification process, background checks and everything. But we have 100,000 carriers that come to our load boards and look at the loads and our recommendations. So the reason why I want to give these numbers is we want to track all this equipment, where it is in real time, and provide recommendations where they need to go, so that, for example, there's a Florida orange season. Everybody needs to go to Florida and pick up the oranges and deliver. But we don't want people to drive empty miles, going to Florida and pick up the things. We want to make sure they're going to Florida, dropping the load, and picking up the oranges and taking it. Similar thing with Amazon Prime. Similar concept with Black Friday. We need to make sure we are optimizing the network in such a way that we have the right trucks and trailer combination or a container combination at right locations. And this chart basically shows the IoT, especially this is true with all our temperature controlled, especially for the one that talks about the cargo conditions. But if you look at any truck that JB Hunt owns, or any of the modern trucks, there are 4 different groups of data we collect. And we are getting these pings constantly in real time, okay, at different frequencies depending on different carriers. JB Hunt gets more frequently, and others may not provide as frequently. We get the driver data, how the driver is doing. Is the driver texting while driving? We know if he is doing it. We know if he is pressing the brakes hard. We know that. If he is taking sharp turns, we know that. We have a very good training program as soon as we observe that behavior to work with the driver and improve their driving habits. We also talk about the power unit, means the truck itself. We know how many miles it drove, what kind of engine oil and other stuff it has, so that when it is due for the maintenance, we know it before anybody can tell us. So we tell the driver, as soon as you deliver the load, take it to the maintenance shop for oil change or whatever that needs to be done. We also have the trailer or the container. So is the trailer loaded? Is it fully loaded, half loaded? And what is happening with the goods within the trailer? So we monitor that. And lastly, the cargo. As I said, the vegetables, pharmaceuticals, and everything needs to be temperature controlled. We need to make sure they're at the right temperature during the whole transit. And some of them also require certain pressure. We need to maintain certain pressure points within the cargo. So I'll stop there because in addition to tracking million trucks on the road, we also need to track a lot of this IoT. They may not be available in every truck, but that's where we want to head. And We already have some of these things working, but with the Neo4j, we want to go more real time. Currently, it's more near real time, and we want to go real time and provide real time insights to our customers and our carriers so that they can make the quick decisions on the fly. So with that, I will hand over to Donovan, who is going to talk about some of the architecture and other things. Is there a question?
Yeah. Do you consider any external data sources like weather, traffic, work conditions?
Yes. For our ETA, arrival conditions, we take into account weather, we take into account traffic, and what speed the truck is going, lots of other things. Yeah. Any other questions? Okay, Donovan, take off.
All right, thanks. All right, so like Srinivas said, we're currently solving a lot of problems, but we want to get faster, we want to get more real time, and we want to get better insights. And we see Neo4j as a huge part of our future drive to continue to do that. So our first major implementation of Neo4j is really around that equipment IoT information. So what led us down the path to selecting Neo4j? We could have put it in a document database. We could have put it in relational databases that we have lying around everywhere. And in fact, some of it is in an invarchar max field, which is wonderful to search and index on, or not, because you can't. So some things that really lend itself well to the graph with our IoT devices and our equipment is that we have a complex nature of equipment to device to operational relationships. What this means is, I don't know how much you guys know about trucks or trucking, but Srinivas talked about you have the power, the truck, what you're driving, right? Behind that, you've got a chassis, which you may have seen as like a flat bed of like nothing. Sometimes you see that driving around. And then you have a container that sits on top of that, right? So those relationships, they're all different types of equipment, and you want to be flexible enough to say that tomorrow, if you decide to start having 2 chassis and 2 containers or multiple containers, or you start doing some type of bulk loads, that you're not constrained by database constraints or a schema that maybe you thought really through a normalization standpoint and then realized your joins are now super complex because these are all equipment, but now I've got a new piece of equipment that I need to join that I didn't even think about before. How do I model that? That becomes very difficult, and these relationships are ephemeral, and then once you start adding the operational relationships on top of that, what am I shipping? Who is this for? Those start to get infinitely more complex and less flexible in other formats. So as we're seeing as a theme throughout the conference, graphs are about relationships, and that's kind of a big thing for us. The other part is schema flexibility, right? We have a lot of different IoT devices. We have a lot of different vendors sending us a lot of different schemas for that data, and we need to be able to ingest it, to enrich it, to understand it, and to persist that in a data store where if tomorrow I'm tracking all new sorts of different information, that I can place it in there without being hindered through a months-long or multi-month-long planning, design, and deployment process. And the other thing that we wanted to do is build a foundation that we can perform data science algorithms off of and things of that nature. When we're talking about routing, obviously finding your shortest path or prioritizing different types of routes depending on what you're trying to achieve. Are you trying to keep the driver happy by getting them home to their family on Saturday? Are you trying to eliminate emissions by taking a greener route than you might take otherwise? There's a lot of things that you can kind of consider and start to see where the built-in data science applications in Neo4j can start to really enable you to answer some of those questions. So we know that we want to start building our foundation in an architecture that's going to allow us to answer those questions as we mature our model. And then the other part is scalability. Lots of equipment, lots of data, like these sensors are sending us tons of readings on a regular basis. So we need a whole lot of stuff, and we don't want to join to like a 3 billion row table to get our sensor data for device A. All right, so what we started looking at for our vision for our equipment graph is that we want to marry our master data, which is metadata about our equipment, whether that's the length of a trailer or the type of truck that we're running. We need to know all of that information to inform us about how we're going to service our operational use of that equipment, which gets into the operational data, which is actually doing the work of shipping stuff, right? Like you want to make sure that you've got a 40-foot container when you need a 40-foot container, a 50-foot when you need a 50-foot, and all sorts of other considerations. You want to make sure that you have a temperature controlled if you are shipping vegetables, right? And then there's the telemetry, which is data generated by the equipment. So all of these kind of work together for our vision of the equipment graph, where we're bringing in operations, telemetry, master data, information about maintenance, which we were talking about previously, and working in our streaming and predictive analytics for our solution. So moving on from the vision, we'll talk about our initial implementation. We got started on this the back half of last year, and we are now running in production with our equipment graph. This is slightly simplified because I really like explicit relationships, but they kind of muddy up PowerPoint slides. So just imagine there's explicit relationships, and we do have some information about our operations graph here. It's just kind of, imagine there's more things here that I can't really share in a presentation because we're focusing on the equipment and the telemetry for the purposes of today. So we've got equipment, which we have multiple labels depending on what type of equipment that is, whether that's power, container, trailer. These pieces of equipment can have one-to-many devices on them, which are providing readings, telemetry readings at regular intervals. And those readings are giving us things like location readings, sensor readings, and alerts themselves. So what we've done is we know that location reading is kind of a well-known structure, right? So when we get those in, we can persist those on a node that's pretty well defined. We understand lat longs and geocoding and stuff like that, but we have a wide variety of different types of sensors. Are you providing temperature information on a zone for the set temperature, the temperature that's going out of that unit, the temperature that's returning? Or are you getting sensor readings about the tire pressure? Or are you getting sensor readings about the RPMs that you're running? So what we did was we created an abstract structure for that in our sensor readings so that we can take those in and still discover those by their types and get that information back and also do any analysis that we need off of it without having a 100% great understanding of what it is 100% of the time. And then those devices will send us alerts, but we also generate our own alerts for this equipment, right? So, and I lose connection to VPN, which is going to be tragic for the demo if it doesn't. Yeah, we'll just, oh no, you. Yeah. Do this, and we'll just connect, and okay. Could not connect. All right, so we may be short on the demo, guys, but I may have a little bit preloaded just in case that happens, so we'll be okay. And then when we talk about the potential changes that we're looking at in order to feed into that vision, we're going to have a metadata graph structure of different nodes and relationships. This operations graph is going to be tied to stops for that service that it's running, the location that it's at, where it's going, so that we can start tying location routes together and start doing that route planning that we were talking about previously through Neo4j as opposed to maybe how we're doing it today. All potential So moving from potential back to today, back to what we're doing, this is a context diagram of our systems that are in place in production today. We have a telemetry enrichment process, which brings in all of those readings from countless different vendors and produces that enriched telemetry to be read into our equipment graph system. We also have that telemetry going into the equipment analytics system, which is, we'll talk about here in a second. And that is going to tie together information from not just the telemetry, but the operational context in order to derive other types of alerts and notifications that we may need to know about. For instance, if you've arrived at a rail yard and your temperature-controlled unit doesn't have enough fuel to sit there until the train picks it up, that might be a problem because you don't want your pharmaceuticals or your vegetables or your mink coats to dip below a certain temperature. And basically what happens from then on is there is an equipment management system that our equipment managers use. And what they want to know is they want to know exactly how their equipment is doing, how it's performing. Is it within the boundaries of what that operational move requires as far as restrictions on those telemetry readings? And then our system also communicates directly with those devices if need be. Here is an example of our kind of one step down from there. This is the architecture that we're currently using in order to ingest and serve up this information. As you'll see, there's the equipment analytics, which is a bunch of KSQL and stuff like that comes in. We'll read that for our alerts, dump it into our graph database. Our graph database gives us information of what is happening right now with our assets. So that same telemetry comes through. We read it from event consumers, some .NET apps. Like we said, everything's running in Kubernetes, drops it into Neo4j. And then we've really had some good engagement from Neo4j as far as not just helping us with the data model, but helping us with the architecture and choosing when and where to use Neo4j. And so they made a really good recommendation of if you're going to have time series databases, probably put that in a time series database. So not only are you getting value out of the product of Neo4j, but when you engage with them, you're going to get a lot of value from the insights on how to use their product, when to use their product, how to be successful with it. And so even though that's not particularly part of what we're talking about today, I wanted to call that out just as something that we really appreciated with our engagement with Neo4j going through this process. And then we make that all visible through a REST API, which interfaces through with the graph database to serve that information up to our equipment managers. All right, so we're going to talk a little bit about some of the mistakes we've made and hopefully share a few laughs and have a really depressingly short demo. But it'll be fine because we're running out of time anyway, so it all works out. So we're going to talk about some mistakes we've made. One thing that I don't have particularly depicted here, but if you'll notice, one of the recommendations is that you make precise updates to your graph, right? Like you get a specific type of event, update a small portion. Right now, we're consuming from one event source and making a very large update, which led us to run into a lot of performance discoveries, which led to a lot of these lessons learned. So the first one, we talk about, or you hear about dense nodes, and that you should avoid them. But what is a dense node and what is not a dense node gets kind of fuzzy. How does that? So originally, we modeled our entity ownership via node relationship, and it seemed like a great idea. You've got like one owner for this equipment, and if you happen to be JB Hunt and you have 300,000 pieces of equipment, that might get a little bit expensive as far as reading. So what we saw was that our query performance and our query plan looked great on its own, but when we started running a lot of these events concurrently, we started to get pessimistic locks, and it became not so great. So we had to kind of move some of that information down into the properties of the equipment itself and expose those as indexes, which if you saw Michael's talk, that's one way to avoid starting at a dense node and working your way down so that your query is keyed off of things that are fast rather than things that are going to hurt. The other thing that we learned very early on was how to improve our query performance through collecting our results. So I don't know how familiar people are with Cypher and writing, what everybody's journey has been at this point. But if you imagine you've got one equipment to many devices to to one telemetry reading to many sensor readings. What you're going to do here is if you're going to return this, you're going to have your one piece of equipment with like a ton of rows, right? So if you're trying to say, give me the 25 equipment I want to look at, and I'm saying I'm going to give you 30 rows per those 25, or you're looking at 250 because you're a fleet manager, that starts to get pretty scary pretty quick. So then we said, okay, well, we'll collect it. Well, that improves performance because then you collect those, condense these into a single row on this equipment. So everything's collected with it, so you use less memory, less rows from your result set. And then we discovered something else that was surprising, which is, like you said, if you've got a one to many, and you start collecting these, you might have collections of collections in your result, which makes it difficult to parse from translating that into an actual class entity or object that you serve back. So becoming familiar with the APOC, the awesome stored procedures available for Neo4j can allow you to kind of flatten that data out so that whether you're pushing this into Excel or your application, it becomes a lot easier to deal with. So the other thing that we had that was kind of funny is our dev deployment went great. Test, awesome. We deployed a prod, no data. Nothing's flowing. In that entire architecture, we're singing messages, boom, boom, boom. They're going through. We don't have any lag on our Kafka infrastructure, and we're like, what is going on? Dynatrace is like, everything's great, man. And so another feature other than profiling is enabling logging on the driver itself when you're using the driver. It's super, super verbose in like the best way. And we actually discovered a lot of our issues. And this particular one was that our change request didn't include the right permission level for our application. So we were denied access. And so we've kind of used this. Like I said, we've got profiling and logging just really go a long way because the profiler for Neo4j is great. So this is an example where we have a 316-line match, merge, delete, all that stuff. Like I said, you got like one event. We're gonna get more refined later, but you know you're gonna start. The query looks something like this, and through using the profiler, we were able to optimize that down to an average of 5 milliseconds per execution, which is doing a lot of databasey stuff in a prior life. That made me feel really good, knowing what that would have cost in a RDBMS land. So anyways, we'll talk a little bit about the results that we've had. So currently, we do about 33 reads and 100 writes per second. And we decided, you know, we should test out to like 300. That'd be good. And then I've got a boss who's kind of tough sometimes, and he basically said like, no, that's not enough. You got to go higher. So then our new target now is how are we going to support 3,000 reads and 1,000 writes with 10 times our current volume. So we'll go through some of the processes that we learned along the way or the results. So current load, 300,000 equipment, 100 requests per second going, or 100 writes per second. Our writes, I can't spell clearly. We're running on Neo4j with 64 gig memory, storage, CPU, and we've got a max pods of 10 on our Kafka cluster and a memory of 2 gig. So when we ran these load tests, we run load, spike, stress, and what's that other one we run? We run different types of performance testing to see if we can break stuff. So what we saw was as pods would scale up, we ate through our current load in production pretty fine, and our CPU usage never got up to 25%. So we were feeling pretty good about that, not too bad. And then we decided to take that 300 pieces of equipment and ramp it up to 300 writes per second, simulating getting more telemetry, because we want more telemetry, we want more data. And once again, starts to spike up, pods spin up, message queues go down, and you'll see that it actually was a little bit better on the CPU. The reason for this being was that our test queries in our first set of data actually created a bunch of extra nodes and relationships that were way more expensive than it needed to be. Rather than repeat the tests like true computer scientists, we just kept going. So it was pretty good. 600K equipment, 600 requests per second. Once again, similar range in CPU. Everything's going good. So then we decided, you know what, this is going great. Let's just bump it right up all the way to the max. And basically our messaging infrastructure died. I'm not too concerned about the Neo4j side, but we may need a little bit of extra horsepower along with our apps and our Kafka infrastructure. But that's fine. And there's supposed to be a demo slide that I didn't put in there, but to show basically that I'm not lying, that we do have this information, I am going to show you fake data. So this is, oh, that's right, and we don't have VPN connection. So this health check, making sure that everything's working. It's not, because I'm not on VPN. And I cheekily got rid of the previous thing. So anyways, just believe me, it's all there. And that about wraps it up for the architecture. You guys got any questions?